the important circuit element is a switch. A switch is basically a two terminal circuit to the element such that there are two states, on state and the off state. When a switch is on, then it should provide a short circuit between its two terminals. On the other hand, when a switch is off, it should provide a perfect open circuit between its two end terminals. So, a switch is basically used to open or close a link between two terminals in a circuit. So, ideally R on equal to 0 and R off equal to infinity. But in reality, we do not have any such switch which satisfies this relationship, and whatever switches we see in practical life, they have a considerable deviation from this ideal behavior. So, MOS transistors essentially act as switches. So, let us see how a MOS transistor can be modeled as a switch. But before we go into a MOS switch, first let us see the model of a real switch and see how it deviates from this ideal behavior. So, this is basically the large signal model of a real switch. So, this figure depicts the large signal model of a real switch. In this model, you can see that when you close the switch, you do not have a perfect short circuit between the terminals, but there is a small voltage drop across a resistance R on. So, this basically accounts for the small voltage drop across the switch when you apply a potential between its ends and close the switch. So, we do not really see the potential at the two end terminals equal, but there is a small drop across the switch which is modeled by this resistance R on. The offset voltage or VOS basically refers to the voltage drop measured across the terminals of the switch when no current is flowing through the switch. Then capacitances CSE and CBSE are basically capacitances from terminals A and B to the ground, and the current, and there is also a leakage current given by IA and IB, which basically indicates the leakages from terminals A and B to the ground. Similarly, when the switch is off, ideally we expect a perfect open circuit between the two end terminals, but in reality it is not open, but a small current actually flows through this through the switch, and therefore it has to be modeled by a very large resistance given by this R off, which is in shunt with the switch. So when the switch is open, current cannot flow through this path, but in lieu of that it basically takes this shunt path to come to this node. So that's why this R off has to be a very high resistance, typically of the order of mega ohms. The capacitance CAB basically indicates the coupling capacitance between these two terminals, and I off gives a measure of the leakage current that flows between the terminals of the switch when the switch is open. Now, when it comes to a MOS transistor, it basically the MOS switch is basically represents a voltage controlled switch like this. This is a voltage control switch. Why? Because you are basically using this control voltage Vc to turn on or turn off the switch between nodes A and B. Now, for this voltage controlled switch, when implemented using a MOS transistor, this R on basically refers to the channel resistance. On the other hand, we do not find this offset voltage. Now, capacitances CSE and CBSE basically refer to bulk to source and bulk to drain capacitances, and the current flowing through the junctions are given by the bulk to source current and the bulk to drain current. And however, we do not find any value for this coupling capacitance between A and B, and therefore, for a MOS transistor we remove this thing. So, this R off basically refers to the subthreshold leakage resistance, and I off basically refers to the subthreshold leakage current. So, below the threshold voltage we normally assume that the drain current to the MOS transistor will be equal to 0, and so, but on the other hand, in reality there is a feeble current that flows between the terminals of the MOS transistor even when the transistor is operating in the cutoff region, and therefore this phenomena is basically modeled by the subthreshold leakage current given by the I sub over here, and the potential drop that occurs because of the flow of the subthreshold leakage current is modeled by this subthreshold resistance R sub over here. The potential that we apply to the gate to turn on the N channel is given by the control voltage Vc. So that is how we typically can estimate the various drops across the switch and what voltage needs to be applied to get what amount of current and all that. One of the problems with these switches is that these switches frequently suffer from two problems. One is the charge injection problem, and the other one is the clock feed through. So, now what is this charge injection? Suppose we have a voltage source delivering charge to a capacitance Cx. Now, the path is basically controlled by a MOS transistor, which is being given a control voltage Vc. Now, when Vc is 1, then this power supply will charge up this capacitor through this switch. But moment this Vc equal to 0, this transistor will go into the cutoff region, and because of this, the charge that was there in the surface of separation between the oxide and the substrate, a part of the charge goes back to the source, and the rest half actually goes back to the capacitance Cx. Now, if you consider this phenomena, then the amount of charge that is going into Cx, it is a very complicated function of this voltage Vc, but as a figure of merit, as a thumb rule, we assume that half of the charge goes back to the source of the voltage and half of the charge basically goes back to the capacitor. So, this is a very crude estimation, but in reality the analysis is much complicated. The other thing is that when we apply a clock signal to the gate of the switch, this clock signal gets because of this clock signal, the gate gets coupled to the source and the drain. So, this leads to considerable issues in clocked circuits, and that is why we try to get rid of both this channel charge injection and the clock feed through problem. The solution is that we can use a CMOS transmission gate or a CMOS pass transistor, and where both these effects are greatly minimized.